Dear students, in this section, we will derive the von Karman Momentum Integral equation. Before proceeding to this equation, we assume you know that the basic concepts of boundary layer concepts applicable for a real fluid. That is a fluid which possesses the viscosity. As well as you know what is done by displacement thickness, momentum thickness, and energy thickness. So you should be aware of this prerequisite before you are going to understand this von Karman momentum integral equation. Let us try to derive this equation. Okay, in between also I will try to recall the basic concepts of boundary layer if needed. So this is a flat plate. This is the leading edge of the flat plate, and I am going to give a uniform velocity profile. This is nothing but the uniform velocity profile with which a fluid is approaching this flat plate. Let this velocity can be either u, or in some books they use as u infinity, which is nothing but free stream velocity. Which is nothing but what? Free stream velocity. So either you can use the term capital U or capital U suffix infinity, which is nothing but free stream velocity. Now the fluid is approaching this flat plate. Because the fluid possesses viscosity, because it's a real fluid, when the fluid is coming and touching this particular flat plate, it forms a boundary layer. This graph what I have drawn is called as what? The boundary layer graph. So what does this boundary layer is nothing but within this boundary layer there's a velocity variation along the flow, along the direction normal to the flow. It's not along the flow, is along the direction normal to the flow. So now where the flow is happening? The flow is happening along the x direction. So where's the variation in the velocity? It will be acting in the y direction. It will be acting in the y direction. That is what I mean to say, that whenever the flow is happening, the velocity gradient will be existing in the direction normal to the flow. So we can see, if I'm going to take a particular location, say A, this particular location, then from this point A, let us call this point as D. I'll tell why we are calling as D rather than B. So we'll call the point as D, and there's a velocity variation from A to D. So here at the wall, the velocity is considered to be 0. At the wall, the fluid cannot pierce the solid, and hence the fluid will stick onto the solid surface, and hence the fluid is brought to rest, and hence the velocity U will be equal to 0. U will be equal to what? 0 at point A. And gradually, because the fluid possesses viscosity, each and every layer try to share off each other. The top layer will try to share off the bottom layer. The bottom layer will try to share off the top layer. So every fluid layer will try to share off each other. So what is viscosity? We have discussed this one, but even then I will repeat once again. The viscosity is also the resistance to flow. Then what is friction? Friction is also resistance to flow. So what is the difference between friction and viscosity? If the friction is caused between the fluid layers, it is called as viscosity. A simple concept. So if the friction is caused between the liquid layers, it is called what? Viscosity. If the friction is caused between a liquid layer and a solid surface, or between two solid surfaces, it is called what? Friction. So viscosity has been experienced by the fluid or the liquid. So it can be for the air also, it can be for the gas also, it can be for the liquid also, like water, air. Every fluid will have some viscosity. Because of this viscosity, they will try to share off each other, and hence there's a velocity variation. And there's a velocity variation. So we can see these velocities keep on varying. So here it is 0. Whatever the velocity at D means, the velocity at D will attain U infinity or capital U. What is the free stream velocity? That is the velocity what I have mentioned here. Let us say here, for example, I am telling the free stream velocity is 20 meters per second. So here the velocity is what? 0. So in between what? The velocity can be say some 9 meters per second. Here it can be what? 18 meters, not 18, maybe 14 meters per second. So at this point D, it need not to be exactly 20. It is enough to have 99.99% of the free stream velocity. So it is 20 into 99.99 by 100. So almost equal to 20 per second. If I'm able to, so approximately speaking, at point D, it will attain a velocity of what? 20 per second. So this height up to which there's a variation in the velocity is called as delta. What is this called as? It is called as delta. What is delta? It is nothing but the boundary layer thickness. This delta is what? Boundary layer thickness. So what is now boundary layer thickness? Boundary layer thickness is nothing but a small region where there is a velocity variation along the normal to the flow direction is known as the boundary layer thickness. Is known as what? Boundary layer thickness. So let me take another point, say B. What will be the boundary layer thickness here? It will be from here to here. So whether this height is more or less, it is definitely more than AD. Let's call this point as C. Now BC is more than what? AD. Then what about BC is called as? BC is also called as what? Delta only. What is BC? BC is also called as what? Delta. What is delta? The boundary layer thickness. What is the boundary layer thickness? The height up to which, or the thickness up to which there is a velocity variation along the normal to the flow, along the direction normal to the flow. So we can see here also the velocity variation is happening, but this height is more. So what do you infer from this? What you can infer from this? The delta. Now, how the delta is, whether it's a constant or varying? Yes, you are right. Delta is varying with respect to what? Delta is varying with respect to x. So delta is a function of x. So if I'm going to have here, what is the value of delta? It's small. When I go here, the delta becomes bigger. When I go still further away, the delta becomes bigger. When I'm going to take this point, say the leading edge point, what is delta? Delta equal to 0. Delta equal to what? 0. So we can see that the boundary layer thickness is a function of x. Let us continue further. For your understanding, I have redrawn the graph. Now, O, B, or the entire distance along the x direction is called the length of the flat plate. It's nothing but a flat plate. This one, what I have drawn is called as what? Flat plate. Flat plate. Now, when the fluid approaches, when the real fluid approaches this flat plate, it tries to form a boundary layer. The boundary layer is given by the red color curve, namely called as what? ODC. Also, we see that the boundary layer thickness is varying with respect to x, and the boundary layer is nothing but the velocity variation along the normal direction to the flow. Here it is along the y direction, and hence we can see because of this one, because of the shear stress tau, there is a variation in the velocity along the y direction. Got it? Now, why this velocity variation is happening along the y direction? Because of the shear stress of the liquid. Here tau is the shear stress. Because of the shear stress, there is a velocity variation along the y direction, that is du by dy. So if you want to make it equal, then tau will be equal to what? Mu into du by dy. So this law is called as Newton's law of viscosity. Newton's law of viscosity. Any fluid which obey this law is called what? Newtonian fluid. And instead of this, generally this power is n. This n equal to 1 means is called as what? Newtonian fluid. If n is not equal to 1 and is less than 1 or more than 1, it is called as what? Non-Newtonian fluid. Non-Newtonian fluid. Now let us assume a fluid which is either Newtonian or not Newtonian, but it is what? A real fluid which has mu, where mu is called as what? Coefficient of dynamic viscosity. For air, it is different. For nitrogen, it is different. For methane, it is different. For water, this value is different. So viscosity is a fluid property. Viscosity is a fluid property. So any fluid which possesses viscosity, when it's going to pass through the flat plate, what will happen? There's a velocity variation along the y direction in a very small region. Whatever I have drawn seems to be very big, but actually is somewhat in millimeters, somewhat in micrometers, even less than that. So this height may be still lesser. In order to understand, we have drawn a bigger size graph. So we've seen that the delta is nothing but the boundary layer, and delta is also a function of x. Now let us take a small control volume of the particular boundary layer region, which is called as what? A, B, C, D. And the length of this boundary layer is delta x. The length of the boundary layer is what? Delta x, which is at x distance from the leading edge. And the total length of this entire plate is L. I will repeat once again. The entire length of the flat plate is L. Let us take a control volume of length delta x, which is at x distance from the leading edge. And let us assume the breadth normal to this board is nothing but B. So if I want to take into a third dimension view, if you want to know what is the surface area, then it will be what? Delta x into B. Delta x into B. That is nothing but the width of the plate, which will be going infinite, but we will take here the width as what? B. Let the width of the plate is B. So these are the terminology which we should know. So now you may ask a question. So what is this von Karman momentum integral equation? This von Karman has derived how much of drag force will be experienced by the fluid by the flat plate. I will repeat once again. Von Karman has established how much of drag force will be experienced by the fluid which is moving on the flat plate. That is nothing but the von Karman equation. Finally, what we are going to find? Finally, we are going to find FD. What is FD? FD is nothing but drag force. What is meant by drag force? The force which resists the flow of this fluid over the flat plate, over the flat plate, over the flat plate. That is the main reason what we are trying to find out here, FD. Okay, now we know that what is shear stress? Shear stress is nothing but force by area. Shear stress is nothing but what? Force by area. I am talking about the shear stress which is acting on the plate, on the control limb at the base of AB. So the shear stress will be equal to FD. I will not put as FD, I will put as delta FD, because FD is the drag force for the entire plate. But I want the drag force only for the elemental length, say delta S. So I am putting delta FD. So what is the area? What is the area which will undergo the drag? The area will be what? Delta X into B. That is the area which will undergo my resistance or the frictional force. Okay, this is the drag force. So this is the area. Okay, so this is delta X into B. So I will put as delta X into B. So from this, what is delta FD? Delta FD will be equal to tau. Okay, so here also it is we can cause tau naught. Why is tau naught? If the CSS is going to be at the wall, near to the wall, then it's not called as tau. It's called either T, tau W or tau naught. We are using tau naught now. So tau naught into area. The area is delta X into B. And generally it's a convention to use negative sign because the drag force will resist the motion. So here, now we try to establish what is von Karman equation. The von Karman equation is used to arrive at the drag force experienced by the flow which is happening over the flat plate. It's happening over the flat plate, and we try to derive an equation for that from the shear stress. Because of shear stress only this drag force is happening. Now we want to know the shear stress at the wall. So it's nothing but what? Tau is nothing but the force by area, shear stress. So it's nothing but what? The force is nothing but the force which is experienced in the length AB. So it's delta FD by the corresponding area. So tau FD equal to minus tau naught into delta X into B. Why this is a negative sign means because it's experiencing a resistance to the flow. Okay. Yes, we will continue further. So tau naught, tau equal to, also we know that tau equal to what? Mu into du by dy. And tau will become tau naught when tau will become tau naught when the distance become at the flat when the distance become 0, that is at y equal to 0, at y equal to 0. So tau naught equal to what? Mu into du by dy at y equal to 0. That's fine. That's fine. So we found that tau naught equal to mu into du by dy at y equal to 0. Now we are trying to formulate another equation for finding the drag force. What is the another equation? Is nothing but from Newton's second law of motion. What is this Newton's second law of motion? Says that the force is directly proportional to the rate of change of momentum. So you know this Newton's second law of momentum, second law of motion. So where P is nothing but what? The product of mass into velocity. So if you're going to put this one, it will be dP by dt of mv. So F will be equal to m into dV by dt, or F will be equal to what? Ma. F equal to what? Ma. So the Newton's second law of motion says the rate of change of momentum will be equal to the force applied, and is acting in the direction of the force. Now we are trying to use this Newton's second law of motion to arrive at the drag force, and we will equate the both these things, and we will try to form the expression. Okay, so let us proceed further. I hope, yeah, let us proceed further. I'll erase even this one. Now I'll draw it once again for your understanding. This is the boundary layer. This is nothing but it is AD, it is BC. This is the control volume. Okay, and this is my leading edge, this one, and this is nothing but my free stream velocity U infinity, or we can also use capital U, or also we can use the capital U. This is nothing but the delta x. This particular distance is nothing but called as my delta x. And the plane which is normal to this one is what? B. And there's a velocity variation along this direction. So now let us take a elemental height. So what will be this elemental height? Let us say this height is dy. Why? The entire length is y. So I'm going to take a small length out of that. So it is dy. So what is the velocity along the x direction? It is u. So you told us a u infinity that I can see the u infinity only above the what? This boundary layer. Below the boundary layer, the velocity will keep on varying. So whenever it's varying, we are keeping a variable. Small u is a variable, whereas capital U is a constant. Capital U is a constant. We can see that the velocity gradient is happening within the boundary layer. So we can see that tau exists within this boundary layer, where tau equal to 0 outside the boundary layer. There's no tau outside the boundary layer. So here the velocity gradient is there. There the velocity gradient will not be there. Here dy by dy is not equal to what? 0. Whereas here the dy by dy is not equal to 0. So within the boundary layer only the stress is happening. Above that, whether the viscosity will be there, definitely viscosity will be there, but du by dy is 0, and hence tau will be equal to 0. And hence what? Tau will be equal to 0. I hope you got it. So now the fluid is coming with the velocity of u. Now what I want to try to form is nothing but the mass flow rate through AD, mass flow through AD of the control volume. So I want to know how much of mass is entering into the control volume ABCD through this left hand side face AD. Through this left hand side face AD. So you know that the mass flow rate is given by what? Rho AV, where rho is the density, A is the area, V is the velocity. V is the velocity. It's not actually mass, it's called mass flow rate because the unit will be kilogram per second and not kilogram. Okay, so now I want to know how much of mass is entering into this control volume through AD. So I will tell this is what? The rho is rho because the density of the fluid. Area, what is the area? Delta x into this, no, not B. Area is nothing but, yeah, it will be B only. It is dy into B, not delta x. It is what? Dy into B. Why I not put delta? I not put a delta, but I put only what? A small element. What does it mean? How much of amount of mass is entering only through this elemental height, not through the entire height. Only through this elemental height is what? Dy into its corresponding breadth. So this is the breadth. So what is the mass which is going to enter into this control volume along the height AD? Along the height AD also we are going to find only within what? Dy. So it's rho into dy into B. So the area will be what? Dy into B. Into the velocity. What is the velocity which is coming? The velocity is u. The velocity is what? U. Sir, why you have taken only dy? Now I can integrate from this point to this point. So what is the point? From 0 to delta. Because y is going to vary from what? 0 to delta. Delta is nothing but what? Your boundary layer thickness. So the next step I am going to put as what? 0 to delta rho B dy into u. Now what is the concept? Now we are not finding the mass only through the small elemental length. I am trying to find for the entire length. So what is the height? It is from 0 to delta. Why is delta? It is nothing but the boundary layer thickness. It is nothing but what? The boundary layer thickness. Which means what? You can take AD anywhere. I have taken AD here, but you can take even AD here. There also to be delta only. There also to be what? Delta only. So what is that? Now we have found out. We have found out how much amount of mass is entering into the control volume A, B, C, D along the left hand side face AD. Initially we found out how much of mass is entering through the elemental strip dy. Then we have integrated from the limits 0 to delta to get the entire mass through the left hand side face, namely what? Your AD. So that is be equal to what? Integral 0 to delta rho into dy into b into your u. I hope you got it. Let us continue further. The amount of mass which is entering into the control volume along the phase AD is given by 0 to delta rho B du into U. That is rho AV. Now let us try to find what is the amount of mass which will be leaving along the across the control volume along the phase B and C. That can be obtained from the Taylor series. Why? Because the Taylor series can be applied when you know the value at the f of x. When now you know the value at f of x. F of x is what? At AD. Now I want to find the value at what? F of x plus delta x, which means I want to find the value at B. Why? Because the distance between A and B is what? Delta x. When the distance is very small, then it's possible to use the Taylor series to obtain the corresponding function at the nearby plane. Here the nearby plane is nothing but what? My BC. Is nothing but what? BC. So now I know what is the mass flow which is entering into the control volume across the phase A. D is gone by some formula. By that, I want to try to take it to the phase, namely BC. Okay, so it will be similar to that. So now the mass which is at AD, the mass flow rate at AD, not AD, it is BC, will be equal to mass flow rate at AC plus dou by dou x of delta x. Dou into dou f by dou x of delta x. Okay, so if you want, I can recall the Taylor series. F of x plus delta x equal to f of x plus dou f by dou x into delta x. Here this is nothing but what? Mass flow rate at BC will be given by what? Mass flow rate at the AC plus dou by dou x of, here the mass flow, here the function in terms of mass flow rate. So into delta x. Okay, that's the concept. So now let us try to find what is the mass flow rate exiting from the control volume through BC is given by, so I have to write the same thing, mass of AC. Mass of AC is nothing but what? 0 to delta rho u into B dy plus dou by dou x of, here you can see there's a dou by dou x of what? The same mass only. What is the mass? Once again is 0 to delta rho u B dy into what? Delta x. So let us call this as equation number 2. Now we found the mass rate entering through AD by normal physics. Then with the help of Taylor series, we found how much of mass will be leaving the control volume across BC. Now the amount of mass which is leaving through 2 is more than which is entering, isn't it? Now entering is less, but leaving is more. Then what is the meaning? Which means certain mass is entering through BC. Got the logic? Let us say once again. Now I am telling here some 3 kg of mass is coming in, or 3 kg per second of mass is coming in, but I am able to get 4 kg per second of mass leaving. Whether it's possible? No. Which means some other mass has been entered. So this mass will be equal to what? 1 kg per second. This mass will be equal to what? 1 kg per second. Then 3 plus 1 will be equal to what? 4. This is nothing but what? Conservation of mass principle. Conservation of mass principle, which corresponds to the kinetic equation. How we got 1? You subtracted BC minus AD, which means I have to subtract 2 minus 1 to know how much amount of mass will be entering into the control volume through the surface DC. Through the surface DC. So I will be writing that also. I will write it here due to the space constraint. So mass flow rate through DC will be equal to mass flow rate through BC minus mass flow rate entering through, here it is leaving, here it is entering through AD. So I can write it here 0 to rho into, 0 to delta rho u B dy plus dou by dou x of 0 to delta rho u B dy in delta x. So this is the amount of mass leaving minus entering. Entering is what? Equation number 1. 2 minus 1. So 0 to delta rho u B into dy. I hope I can erase the other things So it will feel easier. So what I did, I subtracted 2 minus 1 to get how much of mass is entering through DC. So this term and this term will get cancelled. So I can see the amount of mass which is entering through DC is given by dou by dou x of 0 to delta rho u b dy into delta x. So let us call this as equation number 1. So we now come to know how much of mass is entering through AD, how much amount of mass is entering through DC, and how much amount of mass is leaving through what? Your BC. The amount of mass of entering through AD is given by 0 to delta rho u into b dy. The amount of mass leaving through BC is obtained by Taylor series, which is equal to 0 to delta rho u b dy plus dou by dou x of 0 to delta into rho b dy into delta x. So the amount of mass which will be coming through DC will be obtained by subtracting 2 minus 1. That is nothing but what? Dou by dou x of 0 to delta rho into u into b dy delta x. I hope it's very clear. Let us continue further. As we had heard the mass rate through AD, BC and DC. So you may be wondering why process is deriving the mass. Our intention is not mass. Our intention is the rate of change of momentum. Because the rate of change of momentum only will give me the force. Okay, so I am not happy with mass. I want to move to the next step called as momentum. So what is momentum? The product of mass into velocity. So I already have the mass now. If I am going to multiply by velocity, I will have the momentum. It is not only called as momentum, it is called as rate of change of momentum. Why means this is not called as mass, it is called as mass flow rate. What is meant by mass flow rate? It is a mass by time. So it is not kg, it is kg per second. So if I am going to multiply kg by second into velocity, so this is nothing but what? Momentum. Momentum by time is nothing but what? Rate of change of momentum. So if I am going to multiply by velocity itself, I will get us what? The rate of change of momentum. So it's enough to multiply by the corresponding velocity to get the momentum. So it's very easy. So mass, it's easy to find out the rate of change of momentum across AD, across BC and across DC. Okay, fine. Let us move now. So already you have the mass. What is the velocity at which it is coming? Along AD, the velocity is not constant, it's a variable. So I am going to multiply by small u. Because the velocity is what? U. So when I multiply the mass, with the mass flow rate, with the velocity, I got the rate of change of momentum across what? AD. Across AD. Now, what will be the rate of change of momentum which will be leaving across BC? So here also I have to multiply by u. Here also I have to multiply by what? U. So this u and u will become what? U squared. This u and u will become what? This also will become what? U squared. This also will become what? U squared. I hope you got it. So I multiply both the terms by u to get the corresponding momentum which is leaving the BC. The rate of change of momentum leaving BC. Similarly, what is the rate of change of momentum across DC? Can anyone tell what is velocity here? Whether small u or capital U or u infinity. Both u infinity and the capital U are same. So whether I use small u or capital U or u infinity. Yes, you are right. We have to use capital U. Why? Because along this boundary layer thickness, the velocities are up almost reaches the free stream velocity. It is what? The free stream velocity is nothing but what? U infinity or capital U. So here I am going to use the capital U notation. So don't put a small u. Here is what? Capital U. Now I know the rate of change of momentum across AD, BC and DC. How I got it? I multiplied by the velocity for the mass flow rates. Now I will apply the same principle. What the same principle you have applied? Yearly you got 3, 1 to 3. Now it will cause what? 4, 5, 6. Now what I am going to find means, I am going to find, I will try to find the rate of change of momentum in the across the control volume. Across the control volume. It's nothing but what? As I told earlier also, the same principle what you applied for the mass. So it's nothing but BC minus AD minus DC. Okay, so it will be what? 5, equation number 5 minus 4 minus 6. Okay, if you can see here also we apply like that only. The equation will be 1, 2, 3. How we got? It will be 2 minus 1 minus 3. We have obtained the mass for 3 by subtracting 2 minus 1. So that is the same concept we are trying to use. So what is the concept we are trying to use? So the rate of change of momentum across the control volume will be equal to the momentum, the rate of change of momentum which is leaving across BC minus the rate of change of momentum entering across AD and the rate of change of momentum entering into what? DC. Whatever we are leaving, we are taking as positive. Whatever is entering, we are taking as what? Negative. Like that also we can understand it. Okay, so subtract this one with this one and this one. So the answer will be, so you can see here, this term and this term will get cancelled because this also what? Rho u squared b dy. Here also what? Rho u squared b dy. Okay, so we have to subtract only from this term, we have to subtract this term. Okay, this one term with this term. It will be dou by dou x of 0 to delta u squared b dy delta x minus 0 to delta x minus dou by dou x of 0 to delta rho small u into capital U. So small u, this is what? Capital U. Capital U is a constant. Small is a variable into b dy delta x. So this is the resultant change of momentum within across the control volume. Across the control volume. Okay. Fine. So when I'm going to subtract this one, what will happen? Dou by dou x is common. 0 to delta is common. Then what we can put as we can even take b dy outside the, I can even take outside the variable because they are constants, b into dy. Okay, so dy, okay. So it will become u squared into dy. Yeah. If you want, we can take delta x outside. Okay. So u squared dy, I have taken u squared dy, b into delta x taken outside, minus small u into capital U, small u into capital U, rho into, sorry, b into delta x taken common. So this also will become dy. Out of these two terms, which we can take as common. So it's b delta x, dou by dou x of 0 to delta. Out of these two terms, we can take what? Dy is common. So it is u squared minus small u, capital U of dy. Okay, yeah. It's nothing but some mathematical work, not more than that. So from this, what I'm going to do means I'm going to interchange. When I'm interchanging, I'll put as minus b delta x dou by dou x of what you put 0 to delta. Instead of this term, I'll put as other way, small u, capital U. Then only I can put a minus sign before. So minus u, small u, capital U minus small u squared of dy. Why I written dy means the limit is because depends upon dy only. Okay, fine. So from these things, what we can take means minus b delta x dou by dou x of 0 to delta. I am going to take u squared as common. When I am taking u squared as common, it will become capital U squared. It will become small u by capital U. So if I am going to multiply, I will end up with what? Small u into capital U minus u squared by capital U squared. So if I am going to multiply with this term, what will happen? U squared, this capital U squared can cancel, only the small u squared will come. So it's very simple mathematics. What I did, I have taken capital U squared as common term for both the terms. So now I can take this term outside. So this will be, somewhere I missed my rho term. So there will be also rho term will also be there. So we can also take the rho term outside. No, rho term cannot be taken outside. Whether the rho can be taken outside or it should be inside. If you're going to consider it compressible, then rho should be inside. But I'm going to consider the fluid as incompressible fluid. So I have the liberty to take it outside. So I'm taking the rho also outside this integral form. So it will become rho. So here also is rho. So here also this rho will come. Here also rho will come. Okay. So when I'm going to take this one, it will become minus rho u squared b delta x dou by dou x of 0 to delta u by capital U minus u squared by capital U squared of dy. Okay, I hope you got it. It's nothing but normal mathematics. There's no physics involved. So we can see here minus rho capital U squared B into delta x 0 dou by dou x of 0 to delta. Out of these two terms, we can take u by u as small u by capital U as common. So it become 1 minus small u by capital U into dy. So what about this term? What about this term is called as, you should know this term. So 0 to delta u by u into 1 minus u by u into dy is called as the momentum thickness. It's called as what? Momentum thickness. So we can write this as minus rho u squared b delta x into dou by dou x of theta, where theta is called as what? Momentum thickness, and the momentum thickness is nothing but this value. I don't repeat once again. This is nothing but what? The momentum thickness. So we got is minus rho u squared b delta x. So what is this value? Is nothing but the rate of change of momentum across the control volume, which will be equal to what? The drag force, which will be equal to the force applied, which will be equal to the force inside this control volume. Now we can see this force or the rate of change of momentum across DC is 0 because there is no drag force experience because the loss remains constant there. And the delta P is also, there's no delta P by delta X across A and B is negligible. So delta P by delta X is also 0, which means that this rate of change of momentum what you obtained through equation number say 7 will be equal to the drag force. Will be equal to the drag force experienced by the elemental length AB. Elemental length what? AB. So the entire drag force will be equal to the rate of change of this momentum. Okay, so we'll complete that also. It'll take another 1 minute. So already we have derived delta FD equal to what? Minus tau naught into B into delta X. Now we get both of these things. So instead of this FD, this is nothing but what? The rate of change of momentum, which will be equal to the force applied. The force is nothing but the drag force. So it's minus tau naught into B into delta X. So minus minus will get cancelled, B get cancelled, delta x get cancelled. So now tau naught by rho u squared, capital U squared, will be equal to what? Dou by dou x of theta, or dou theta by dou x. So this equation is called as von Karman Momentum Integral equation. Where is integration? The integration is hidden inside theta. Theta is nothing but what? 0 to delta of 1 by u by u of 1 minus u by u into dy. So don't worry about this integral form. Still it is integral form only because theta has what? Integral. So this von Karman equation is already for the incompressible fluid, and hence it is called what? Von Karman Momentum Integral equation. Okay. So we'll continue further. This is nothing but the von Karman's momentum integral equation. This equation. So generally, we can define local coefficient of drag CD as tau naught by half rho u squared, where CD star is called as local coefficient of drag. Why is called as coefficient? Because this will become what? Non-dimensional. And generally it is admissible to divide by 1 by 2 because the general convention used worldwide, and also useful for other forms. So it's always better to divide by 1 by 2. So tau naught by half rho u squared, and this become what? Local coefficient of drag. But generally people are not happy with the local coefficient of drag. Generally they will go with the average coefficient of drag called as CD. What you have to do means, what is tau? Tau naught is nothing but what? Force by area. That's it. So for what is force? The force is nothing but my FD. So FD by half rho A into U square. Got it? What is the difference between this and this one? Just instead of tau naught, I associate as what? Force by area. What is the force? It's nothing but what? Drag force. If it's going to be elemental length, then it will be delta FD. If it's for the entire length, it will be FD. Okay, so FD will be FD divided by half rho U squared. This value is called as, this is generally called as what? Coefficient of drag. This is not generally, they are not considering. but both are same only. Here they are considering as what? Average coefficient of drag. Average coefficient of drag. So this is the CD. So what is the main purpose of doing this one Karman equation? To determine the drag force. So if you want this drag force, you can find it out. You can find out in the exam they will ask you to find the drag force. Then you should know the CD value. Then multiply with this value, you'll get the drag force expressed by the flow over the flat plate. Okay. How to get this FD? Then we have to go once again the shear stress and we have to do all other works. But it's simple only. I hope you enjoyed the session. And in the further class, we'll try to arrive at various applications of this von Karman momentum integral equation. So one more thing is, if you found FD is nothing but minus tau naught into B into delta x. This is not FD, it's called delta FD. That is for the elemental length. If you want to find the drag force for the entire length, then what do you have to do? What do you have to integrate? Yeah, it is 0 to delta or 0 to L. 0 to delta along the y direction. We are not worried about the y direction. We are worried about the drag force which is happening on the surface. So it is 0 to capital L. Well, capital L is the length of the plate. So minus tau naught into B into delta x. So using this formula, you can calculate the drag force over the entire flat plate. This is the drag force which is expressed by the elemental length delta x. This should also be considered. Thank you.